Whenever someone says about the motor, the image that comes to mind is usually something spinning, right? However, packaging and CNC machine requires motor with linear movement. In the next part of this presentation, we are going to learn about this motor by understanding a crucial concept about the linearly traveling magnetic field. In this project, our main objective is to demonstrate the effect of a linearly moving magnetic field. Here we created a model of a train represented as an aluminum sheet, and also we use the consequent pole changing method to change the speed and interchanging two phases to change the direction. At first, we will see the theory behind the working of motor. Then we will cover the theories behind the speed and direction change of this three-phase linear induction motor. Then we will show the project that we created.
A linear induction motor operates using the same principle as conventional induction motor. It is composed of two parts, the primary and the secondary, which interact with each other only when power is applied. Conventional three-phase induction motor uses the three-phase voltage to create a rotating magnetic field. If we cut an induction motor and expand it, we get a linear induction motor. When three-phase AC power is applied to the primary, a traveling electromagnetic flash wave is induced and moves relative to the primary. This wave induces an electric current in the conductive reaction plate. The induced electric current interacts with the magnetic flux to produce a linear force. The speed of the motor can be varied by changing the input frequency.
Here we take a simple configuration of three coils supplying three-phase voltage. We need to find the variation of magnetic field due to the variation of current. In this plot, we take three instances. Here, based on the current direction, we can predict the field lines according to the right-hand thumb rules. Using this, we can predict magnetic field line at this first instant as shown in this picture. Similarly, for the second and third instance, we get this and this magnetic field. After this, if we only take the magnetic field and compare all three instances, we can clearly see that in each instance, the orientation of south and north pole is shifting slightly towards the right.
We continue our analysis here. We are seeing that the magnetic field is moving linearly. After going to some distances to the right, a new north-south pole is appearing in left. But at the same time, the south-north pole has disappeared from the right. Then the north-south pole has continued its motion towards the right side. So this motor works basically on the concepts of linearly traveling magnetic field. Now when we place an aluminum block in this varying magnetic field, an EMF will be induced in this block according to the Faraday's law. An eddy current will also start to flow here, and this induced eddy current will follow the Lenz's law. Now, if we analyze the force acting on the block, we will see that the force is basically following the direction of the linearly traveling magnetic field. The motor we have built so far is directing the contacting bar from left to right. Now if we want to change the direction of the bar, we have to reverse the motion of the magnetic field. To do so, the order of the three-phase power supply has to be changed. And then the contacting bar will move towards the left.
One of our goals in this project is to perform a very basic method of speed control, that is the method of consequent pole changing. It relies on the fact that the speed of the field, or indirectly the speed of the rotor, is inversely proportional to the number of poles, which can easily be changed by a fraction of 2:1. Here we have two pictures of same two pair of coils. In this picture, this coil has a counterclockwise rotating current and this coil has a clockwise rotating current. If we use our right hand rule, we get a north pole here and a south pole here, hence a two pole machine. In this picture, we have a counterclockwise rotating current here, but also a counterclockwise rotating current here. So we get two north poles in these coils. Because of these two north poles, we get two weak south poles here. hence a 4-pole machine. From our theory, we can say this configuration will have half the velocity of this configuration. In our project, we also have two sets of three-phase coil. In this coil, we have counterclockwise rotating current, and in this coil, we have a clockwise rotating current. Because of this, here we have a north pole and here we have a south pole, hence a two-pole machine. But in this configuration, we have a counterclockwise rotating current here, also a counterclockwise rotating current here. So we get a north pole here and a north pole here also. Because of these two north poles, we get a south pole here and a south pole there, hence a 4-pole machine. So this configuration should have half the speed of the configuration before.
Now we will talk about the process of constructing our project. After building the stator, we insulated it and then finished the winding. To build the core, we used laminated E-core by adding them side by side. This particular E-core was used to reduce eddy current loss. We used 27 gauge copper wire for our windings. Aluminium sheet was used as the rotor, where laminated E-core acts as the stator. To connect everything properly, we used nuts and bolts. Insulating paper helped to avoid connection risk, and tape was used to insulate the shorted copper wire connections.
Description of the constructed linear induction motor. Here we made a three-phase linear induction motor. We have two coils per phase. This is phase A, this is phase B, and here is phase C. Now this is the input terminal of coil 1. This is the output terminal of coil 1. These are the terminals of coil 2. Three-phase power supply will be connected with our input terminal of coil 1. The output terminal of coil 1 will be connected to either of the terminals of coil 2. The unconnected terminal of coil 2 will be shorted and act as our neutral point. Changing the speed of the machine. In order to change the speed, we used consequent pole changing method. We applied both 2-pole and 4-pole configuration. Here at first we will see a 2-pole configuration. The coils are winded counterclockwise, starting from this terminal ending in this terminal. There are 80 turns per coil. When the power supply is connected to the input terminal of coil 1, we get a counterclockwise current flow in each phase of coil 1. If output terminal is connected to the terminals marked with black tape, then the current direction in coil 2 is clockwise. The terminals left will be shorted together and act as a neutral point. Thus, the current is flowing counterclockwise in coil 1 and clockwise in coil 2. We get a north pole in coil 1 and a south pole in coil 2. Now, we will observe the operation of motor in 2-pole configuration. Now we shall proceed to 4-pole configuration. Input terminals will be as it was, however, the output terminal will be connected to that terminal of coil 2. The other terminal of coil 2 will be shorted and will act as a neutral point. Then, the current flow in both the coils will be counterclockwise. Therefore, two north poles will be created in both the coils per phase. Due to the north poles, we will get two consequent weak south poles in both the coils. Again, current flow in both the coils will be counterclockwise, and as a result, two north poles are created in both the coils, and two consequent weak south poles will be created per phase as well. Now, we shall observe the operation of the motor in 4-pole configuration. We know speed is inversely proportional to the number of poles. We observed the same phenomena from our experiment. The speed in case of 2-pole configuration was higher than that of 4-pole configuration. In order to change the direction of transition, we swapped two of the phases.
We are from group 5. This concludes our presentation. Thank you everyone for listening.